Yes, good afternoon. Am I audible?
Yes, sir.
Okay. Yeah.
Afternoon.
Yeah, good afternoon. Yesterday we started with the nonlinear data structures. You understood what are trees and how trees are represented. And then you also understood how to construct a binary search tree. Okay. One example I showed you. So now today, okay, uh, because majority of the lab batches they are doing 8th program today. So 7th they have already completed and 8th they are doing now. So if I don't give any lab program this week, then you won't be having anything to execute for the next week. Okay. With that intention in mind, so I'm just planning to explain you the polynomial program. Okay. Theory behind that is already explained to you people in the module 3. Okay. Before I let me share my screen. So before I go for the program, so let me just recap the polynomial operations or the polynomial addition, okay, using the linked list, so which we have already discussed, and it will be a small recap before going to the program. Okay. Okay, I hope all of you remember this example which we discussed earlier when we were discussing the singly linked list. So we understood this as an example also. Okay, polynomial representation. So when I say polynomial, it has two things. One is the coefficient and exponent, and a self-referential link in order to point to itself, or it holds the address of the next node which is holding the coefficient and the exponent. And then polypointer, see this polypointer is an alias name to struct polynode, and since I've used the star here, now polypointer is acting as a pointer to this struct polynode. Okay, so if I create any variable using this polypointer, so they act as a pointer to the struct polynode. So now polypointer a, B, C I have given. Now all these A, B, C, so they are acting as pointers to this struct polynode. And then here I have also shown the structure of the node to represent the polynomial. So one term of a polynomial. So it is something like this. You require one field for storing the coefficient, another field for storing the exponent, and one more field for storing the address of the next node which is holding the details of the next term in the polynomial, say the coefficient of the next term and the exponent of the next term. And then we went through an example, we took an example. Okay, this is a polynomial and this is b polynomial. So if you just look into this polynomial, so there are three terms in this polynomial, and for the term 1, so 3 is the coefficient and 14 is the exponent. And similarly for the term 2, 2 is the coefficient and 8 is the exponent. And if I take the last term, 1 is the coefficient and exponent is 0. Okay, and if there is no exponent component present, so then the exponent is 0, because anything to the power 0 is treated as 1. And so similarly I have the other polynomial also with 3 terms, and you can notice here the coefficients and the exponents of each term. Now this polynomial, how it is represented, in the form of a singly linked list, it is represented something like this. So A is a pointer which is because A is a pointer which is pointing to the struct polynode, and this is one struct polynode which holds one term of the polynomial. A is pointing to this, and then so 3 is the coefficient stored here, 14 is the exponent stored here, and this is the link field holding the address of this node. So this is how the polynomial can be represented by using a singly linked list. Okay, and similarly the other polynomial also represented in the form of a singly linked list, and you can observe the link field of the last node is set to null because they are the last node. There are no more terms after this. And then I also explained you how to add two polynomials. Say a polynomial A is pointing to this node, and this is the first term of the second polynomial, and this is the first term of the first polynomial. Now what we do now, we compare the exponents of the terms. So I am taking the exponent of the first term and I am taking the exponent of the second term. So A arrow exponent and B arrow exponent. Now when I compare them, they are same. If the exponents are same, then I go for adding the corresponding coefficients. Okay, so that is what is done here. Okay, 8 plus, so 3 plus 8 is 11. If exponents of both the polynomials are same, both the terms are same, then add the corresponding coefficients, write the same exponent. Okay, this is what the resultant node in the resultant polynomial. Okay, and similarly, in case after doing this, what I do, I go for incrementing both A and B. So A is incremented and made to point to this, and B is also incremented and made to point to this, and that is the status what you are seeing here. Okay, both A and B, they are incremented. Now here I again go for comparing the exponent of the second term and exponent of the second term in the second polynomial. Now when I compare here, they are not same. Okay, one is 8, so the exponent of the second term in the second polynomial is 10, and they are not same. Now what to do in this case? So you just compare, okay, whether the exponent of A is less than exponent of B. If exponent of A is lesser than the exponent of B, then, or in other words, I'll tell you, so go for retaining the coefficient of the term whose exponent is higher. Now here for this term, the exponent is higher than compared to the term of second term of the polynomial 1. I am retaining the, yes, please mute. Please mute. Mute. Okay, thank you. See, I am the exponent of the coefficient of the highest exponent is retained, and so this one, the exponent of the highest term is also written. The highest exponent is written. Okay, so this is what you do. If they are not same, so just go for retaining the exponent and coefficient of the term which has the highest exponent. Okay, now among these two, so this term has got the highest exponent, and the same thing is retained over here. Okay, next what you do? So next, so since we retained this term as it is, so we are not going to increment A, we are going to increment only B. B gets incremented, and that status is depicted here. Okay, A is still there only, and B is pointing to this. And next, when I start comparing, so if I just observe now, the exponent of the term A is greater than the exponent of the term B. Now what is that you need to do? You got to retain the coefficient of this term and exponent of this term. Okay, 2, 8. So that is what? 2 and 8. and D is pointing to this. Now we make B point here itself and only A gets incremented, and this process we repeat until we reach the end of the polynomials. And this was explained earlier also and now also, because we are going to discuss the implementation of the same, and even the implementation was also discussed earlier. So this is what the implementation is. Okay, so this is same what we are doing. We are creating the front, rear and temp. So but earlier we took it as ABC, now we are taking it as front, rear and temp, no problem. And then allocating the memory, and then we are comparing here. Just observe here, compare A arrow exponent and B arrow exponent. So the switching is happening based on the return value from compare, and all of you know that compare is going to return the value 0 if both the exponents are same. Okay, if the return value is 0 here, case 0, what is that we are doing? We are adding, summing the corresponding coefficients, and then you can go for attaching the exponent of any one of the term, because both the terms have the same exponent, and then go for incrementing both A as well as B. So in case the exponent of A is bigger than the exponent of B, then what is that you got to do? So this is what you got to do. So you got to retain the coefficient or attach the coefficient of A and exponent of A and increment only A. So don't do anything to B. Similarly, if exponent of B is higher than exponent of A, then what you do? You retain the coefficient and the exponent of B and increment only B, and don't do anything to A. And this was discussed earlier, and the same thing we are going to implement now. Okay, hope all of you can recall this, which was explained earlier, and now also I have refreshed it to some extent. Is that clear?
Yes, sir.
Yeah. So now we'll go here. Seven, 8, yeah, 9. Observe now. So design, develop and implement a program in C for the following operations on singly circular linked list, SCLL, with header nodes. So but here we understood with this polynomial addition by using a singly linked list. So it was not a circular singly linked list, it was just a normal singly linked list, and even without the header node also. So we didn't consider any header node here. But what the problem is saying is you got to implement this polynomial addition by using a circular singly linked list. Now circular singly linked list is already clearly explained to you people. So instead of storing null in the last link field of the last node, we store the address of the first node. Okay, so they will be having a pointer connection, something like this. So that is what a circular singly linked list. And along with this, so you'll be having an header node also. Okay, the starting node or the header node, what we call it as. Now using that, you should go for implementing this addition of polynomials. Okay, with header nodes. Okay, and now represent and evaluate the polynomial. So you can just observe now. So the polynomial what we are taking, the example when I discussed, it add only one term, okay, that is exponent term. Now here the coefficient is 6 and I have 3, x, y and z, x to the power 2, y to the power 2 and z, and then so here x is not there. So this is what the polynomial given, okay. So find the sum of two polynomials, that is poly 1 of xyz and poly 2 of xyz, and store the result in polysum xyz, okay. So these are the two polynomials now. So the polynomial here, it's little bit complicated than compared to the polynomial what we understood here, because here I add only one exponent component, that is x to the power 14, but in the lab program, in addition to this x, we have y and z as well, okay. Now you got to find the sum of two polynomials, that is take two polynomials, something like this, okay. One you are calling it as poly 1 and the other one you are calling it as poly 2. You got to find the sum and it has to be stored in another list called as polysum, okay. Yeah, and support the program with appropriate function for each of the above operations. Any doubts?
No, sir.
Okay. Okay. Next is so just a minute. Okay. Do I need to zoom the program, or this is fine?
Fine, sir.
Okay, this is okay thing. Okay. Now, see again, we are creating a poly list. Now inside this, you can have look at the members. Okay, int coefficient. So because I need one member to store the coefficients, can I know this? And then three integer members x, y, and z for storing the exponents of x, y, and z. Okay, they store the, so this x stores the exponent and of x, and y stores the exponent of y, and z stores the exponent of z. And then float SAL also is there. I'll tell why this is used later. And then self-referential link, which is the link field and which holds the address of the next node in the poly list. Okay, and then I have created a type definition to this struct poly list as a star node, and whenever I want to declare a pointer to this poly list, I just say node space and give some variable name, and that creates the pointer to this poly list. Okay, instead of every time to create the pointer to the poly list, writing it as struct poly list star some variable name, so in future I can go for using this node. If I just say node and then some pointer name, so it is a pointer to this poly list. And then this all of you are very much clear, the malloc function, which is used to dynamically allocate the memory. So this is not a function, sorry, this is a macro for dynamically allocating the memory. Okay, And then we have few prototypes in our program, function prototypes, because these are all the user defined functions which are there in our program. One function is read poly, because before performing any polynomial addition, okay, you got to read the polynomial. Okay, how to read the polynomial? I read the polynomial by making a call to read poly, and this is an user defined function, and one argument it takes. What is that argument is pointer to the struct poly list, and what it returns is address of the node, or what it returns is a pointer to the struct poly list. Okay. So that is one function, and similarly we have other function which does the polynomial addition. Okay, p add is nothing but the polynomial addition, and you all know to perform the polynomial addition you require two polynomials. To one first polynomial we have a pointing, and to the second polynomial you have b pointing. And finally, after performing the addition of these two polynomials, what p add returns is another address of another polynomial. Okay, and then float eval poly. So within this p add, I go for calling eval poly. Okay, so because first I call p add and I get the required terms from both the polynomials, and to perform the addition operation, okay, and the shifting of the variables of the polynomials, I make use of eval poly. Okay, and after evaluating and adding the two terms of the polynomials, so the polynomial, the new term, of or the term of the resultant polynomial should be attached to the resultant polynomial. Now, what is that resultant polynomial? I have taken one more this thing here. What is it? I'll just show you. Yeah, and the question says, so the resultant polynomial should be stored into a separate circular singly linked list, that is polysum. Now, using this, I am attaching the resultant node to the polysum. Okay, so when we go to these functions, we'll understand. So finally, after attaching every resultant term to the polysum circular list, next I should go for printing the same. Okay, so the resultant polynomial can be printed by using print poly, and what we are passing to that is again the address of the first node of the resultant polynomial, or the resultant singly circular list. Is that clear till here? Have you people got an idea why these functions are required? And these are the prototypes. So any doubts in this prototypes, what I told you now?
No, sir.
Okay. Now, so into the main, inside the main I have declared 3 pointers to struct poly list. Okay, p1 is a pointer, p2 is another pointer, and p3 is one more pointer. Now, as usual, similar to the other programs what you have understood, so we have the flag variable done, initialized to 0, and then choice, okay, and then float result, because we compute the result, by comparing the exponents of the two polynomials. We go for adding. Okay, now when we add, we get the result, and to hold that I have one floating point variable created, and to read the exponent of x, exponent of y, and exponent of z, I have the local variables created expx, expy, and expz. While not done, so same similar to the previous programs. So not done as 0, initially done has taken the value 0, not of 0 is 1, so we enter into the while loop, and then go for printing this options. So we have 3 options here. One is polynomial evaluation, another one is add polynomial, and the third option is for exiting from the program. Okay, Now, enter the choice. I'll read, and if it is eval polynomial, okay, so case 1, so it makes a call to eval polynomial, okay, and then go for finally go for printing the result, okay. So this one. Now what we will do is, so we'll just start with this add polynomial, okay. Case, okay, let me go to eval poly. So what eval poly function will do is, it will go for evaluating the given polynomial, that's all. Now I'll just go to the function eval polynomial. Yeah. So here is the function eval polynomial. Now what we are doing here, so some variable I have taken initialized to 0. I have taken 2 pointers to my struct polylist, one is p, another one is start. So declare 3 local variables again, x value, y value and z value, and then I have the number of terms as 20, okay. In terms of 20, these are all the coefficient of those terms, okay. You can just observe here, these are all the coefficients of those terms. This is 6, 2, 2, 1, minus 4, so many terms I have. Now I am allocating the memory, okay, size of polylist node, the node gets allocated, and then p arrow link is equal to p, okay. So p, that means since you have to make it as a circular list, so after the node gets created, so who will be pointing to it? P will be pointing to it, and the link field of the p should be made to hold its own address, okay. This I have already shown you people how to do it. So if you want me to write, I can write and show you. So I'll just go to slideshow. So this is what we are doing. You create a node and p is pointing to this. Now what is the meaning of p arrow link is equal to p? Okay, p arrow link is this. So p is pointing to this. P arrow link is this field. Now what is that I need to do? When you create a node for the first time, what is that you need to store here? So address of its own node. Okay. So p is equal to, sorry, p arrow link is equal to p. Okay. Here in this field, I am storing its own address. Something like this. Okay. So that is what we are doing here. I'll just escape this now. See, p arrow link is equal to p, and then enter the value of x, y and z. Okay, I am reading the x value, y value and z value. Okay, so x value, y value and z value. Next, what we are doing here, for k is equal to 0, k k less than n, k is equal to k plus 4 we are doing. Okay, so why we are doing k plus 4? Because each has how many terms here? See, so this belongs to, so this is the coefficient. Okay, and then coefficient of what? First term. Okay, so this is 4 you have to skip. This is x and this is y and this is z. Okay, 4 you got to skip, and next you have to take from here, and next 4. Okay, and next 4. So that is why k is equal to k plus 4. Now every time we are doing this, attach the term k plus 1, term k plus 2, term k plus 3 to the polynomial. Okay, and then what you do, so make start also to point to the same node where p is pointing, and then p is equal to p arrow link. So what we are doing here, we are basically building the circular list. Okay, building the circular list of all the polynomial terms with these exponent values. Now once you do that, so this is where you are evaluating. Now how you are evaluating, just look here. Sum is equal to sum plus p arrow coefficient you are accessing, and power x value to the power x. Okay, so I am reading the x value here, x value to the power x. So the exponents are read here. I will just show you. Sorry, it is this x value dot p. 1 second. So it is underlined in red. Sorry. So this is x value, comma p arrow x. Okay. So x value, whatever I give, that to the power p arrow x. Okay. So I am finding the power, multiply by, so y value into p to the p y exponent into z value into z exponent, okay, to the power z exponent. I get the sum. Okay, and I keep doing this for all the nodes. Okay, I keep doing this for all the nodes, and finally when it is done for all the nodes, I am out of this and I say return sum. So this is basically evaluating a given polynomial. That's all. Okay, I'll just show you here. So eval poly, it comes here, and then these are the coefficients. Okay, and then here you are reading the values of x, y and z, and then so attach the terms. Okay, this is I'll just show you here. This is k, this is k plus 1, and this is k plus 2, and this is k plus 3. Okay, everything you are attaching, and then the respective powers, coefficient you are multiplying, and then the powers you are computing. Okay, so and finally you get the sum, and that sum is being returned. So this is only evaluating a given polynomial. Now adding two polynomials, that is case 2. So and finally result will be returned, and it is going to print you the result. Now case 2 is adding two polynomials. Now you require two polynomials, and you should go for reading two polynomials here. So first I am allocating the memory. So size of struct poly, and p1 is pointing to the first node and p2 is pointing to the second node. Since they have to be made circular, I am saying p1 arrow link is equal to p1 and p2 arrow link is equal to p2. OP people understood this?
Yes, sir.
Okay.
Yes, sir.
So you are making it as circular. Okay. So I hope evaluating a polynomial is clear. Now this. So allocate the memory for the first polynomial. So allocate the memory for the term in the second polynomial. So make p1 will be pointing to the first node and p2 will be pointing to the second node, and you are making the link field of both the nodes point to itself. Next, you are going for reading the polynomial. Enter the polynomial a first polynomial. So which pointer you got to pass? So I want P1 to be pointing to the first polynomial. Now I am passing to read poly, I am passing P1. Okay. So similarly, I go for reading the polynomial B, same function, but what I am passing is P2. Okay. Now we'll go to read polynomial. Say read polynomial is this. Now here you are reading the complete thing. Okay. Even the coefficient also you are reading. But evaluating the polynomial, coefficients you are not reading. Coefficients were written directly inside the program. I'll just show you. Yeah. So these were the coefficients what we had written. Okay. Like this, maximum you can go for giving up to how many? 20 terms. Okay. But here for adding the polynomials, we are reading the coefficient, we are reading the exponent, everything we are reading. Okay, here. So we come here for read poly, and then please, your voice is breaking. Hello? Please repeat again. Hello? Okay, please feel free to stop me when your network issue is resolved. Okay. Okay. Read poly int this one. CE is the coefficient, exponent of x, exponent of y, and exponent of z. Now inside the while loop, I am reading enter the coefficient and exponent of x, y, and z. So everything I am reading. I am reading them as integers. Now coefficient I am reading it to the variable CE, exponent of x I am reading it to exp of x, exponent of y I am reading it to exp of y, and similarly z for exp of exp z. Now I check if exponent of x is equal to -1, okay, and then I am going to break. Okay. Now otherwise I attach, okay, this coefficient, because what is the meaning of attaching? Attaching is nothing but adding it to the circular singly linked list. Okay. Now who was pointing to the circular singly linked list? For the first polynomial, P1 was pointing, but when I passed P1 as argument to read poly, so P is also pointing to the same node where P1 is pointing. Now using P, I am attaching, I am calling attach, and then the return value from attach is being assigned to P. Nothing but P points to the same node where P1 is pointing. Now let us go to the attach and see how it is written. See, attach. Attach is nothing but preparing here a node. See here. So node 2 pointers, one temporary pointer with the name temp, and Q is taken, allocating the memory. Now observe here. So using this temp, so temp will be pointing to the node that is created. Using the temp, I am assigning the coefficient field is equal to C, because here the formal parameter is C. So but while passing, we passed it as C. I'll show you. So we passed it as C. This is the actual parameter, but the formal parameter name is what? C. Okay. So temp arrow coefficient is equal to C, and this coefficient is from this is the member of the struct poly list, and temp arrow x is equal to, I am storing this exponent of x, and similarly exponent of y to the member y, and exponent of z to the member z. And next, see, add arrow link. Okay, add arrow link is equal to, sorry, q is equal to header arrow link. We are making q also to point to the same node. Okay. So this is header what we have passed. Next, what I am doing here, while q arrow link not equal to header, so that means if it is not the same node. Okay. So if it is not the same node, so or the words, if it is not the first node which we are creating, then I keep incrementing the queue until I reach the end of the circular singly linked list. So if it is the first node, okay, So I skip this step and I make q arrow link is equal to temp. Okay, so q is pointing to the first node that is created right now, and q arrow temp, so q arrow link is equal to temp. So temp was pointing to what new node, and q was pointing to the header node. So when I say q arrow link is equal to temp, the link is established between the new node which is created and the header node. Okay, and then temp arrow link is equal to header and return header. So I think I need to write and show you people for a better understanding. So let me ask you whether you people understood this part or not. So you want me to write it in the form of the diagrammatic representation and show you, or are you able to analyze and track it? Now, when I am explaining all these statements, you should mentally imagine the diagrammatic representation, then you'll get to understand. Otherwise, so blindly if you sit and listen, you'll not understand anything. Now even when I was explaining, I was mentally imagining those pictorial representation, so then I can easily get into the concept. So I want you people to try the same, because for each and everything, if I keep writing the pictorial representation and relate that with the code, it takes more time. So I need your response on this, please.
We are able to understand like this one.
Okay. So what you have to do is just take a piece of paper and a pen keep a piece of paper and a pen next to your laptop. So just keep writing all these things in the pictorial representation, then you can easily imagine those things. Okay, that is what. So basically attaching a node to a circular singly linked list, and this process we repeat for all the terms. Say for example, in my polynomial 1 I need 3 terms, and this is going to repeat for 3 times. Okay, so next is, so that is what is reading the polynomial. Similarly we go for reading the second polynomial also. See, after reading the first polynomial, so finally you have p1 pointing to it. So next you go for reading the polynomial b, and when you, the same function again, when you read the polynomial b completely, so p2 will be pointing to it. So next is adding those two polynomials p1 and p2. So you do that by making a call to p add. Okay, so polynomial addition, and you're passing the address of the first node from the first polynomial, which is nothing but p1, and address of the second polynomial, which is nothing but p2. Okay, so now we'll go to p add. Yeah, so observe now. So p add, so p1 is pointing to the first node of the first polynomial, and p2 is pointing to the first node of the second polynomial. Now inside this function p add, I have taken another pointer p3. Now, and this pointer p3 is for the resultant polynomial, because after adding two polynomials I got to store it into the resultant polynomial, right? For that purpose I have taken p3. And here start a is equal to p1 and start b is equal to p2. So now what start a is doing? Start a is a pointer again to the poly list, and where it is pointing? It is pointing to the same node where p1 is pointing. Right now, to the first node of the first polynomial, there are two pointers pointing. One is p1, another one is start a. And similarly, when I say start b is equal to p2, you have start b and p2, both the pointers pointing to the first node of the second polynomial. Now here, so before I go for performing the addition of the corresponding terms from both the polynomials, I got to allocate memory for holding the result. Okay, so malloc I'm calling again, the macro malloc is being called here. So p3 is the pointer which I'm passing, because to the newly created node I want p3 to point. Okay, P3 size of struct polylist and then node. Okay, so after that P3 is created. Since you got to make it as circular, see, observe what you are doing. P arrow link is equal to P3. So you are making the link field of P3 hold the address of itself. Okay, so I hope you can imagine that. Now what you are doing, see, start A is already pointing to the first node of the first polynomial, and start B is also pointing to the first node of the second polynomial. Now what I am doing, I am just increasing, I am saying P1 is equal to P1 arrow link. Okay, so why I am doing this, because the first node, when you create the polynomial, the first node here is the header node. I don't want the header node, I need to skip the header node. Now, and start B is pointing to what? The header node. Start A and start B are pointing to the header node, but I don't want P1 and P2 to point to the header nodes. Instead, I want them to point to the first terms of my polynomial. Now, how do I make them point to the first terms of my polynomial? Just by saying P1 is equal to P1 arrow link. So now P1 is pointing to the first term, and it has skipped. Earlier it was pointing to the header node, now it is pointing to the first term of your polynomial. And similarly, P2 is equal to P2 arrow link will make P2 to point to the first term of the second polynomial instead of pointing to what? The header node. Next, so while P1 not equal to start and P2 not equal to start B, P1 not equal to start A and P2 not equal to start B. Yes, condition is true. So P1 is not pointing to the same node to which start A is pointing now. Yes or no? Start A is pointing to the header node and P1 is pointing to the next node after the header node. Hope you people are following?
Yes, sir.
Yeah. And then when I check, so it's a AND operation, correct? No? Both should be true. So even P2 should also not pointing to what? Start B. So P2 not equal to start B. Yes, true. P2 is pointing to the first node, first term, and it is not pointing to the same node as the start B, because this is justified because of these two statements. Okay, next. Inside that, okay, P1 is pointing to the first term of the first polynomial and P2 is pointing to the second term of the second polynomial. Now what is that you got to do now? See, you got to check. So here, this logic, what we did here, we started comparing the exponent of what? Both the terms. If exponents are same, what is that we do? We add the corresponding coefficients. So same thing we are doing here. I am just comparing the exponent of exponent of P1, okay, x exponent of P1 with x exponent of what? P2. And there are three things here, x, y and z. I should be comparing the exponents of all x, y and z. I am just checking whether they are equal. And here also I am checking the y exponent of P1 is equal to y exponent of P2 and z exponent of P1 is equal to z exponent of P2. If all of them are same, okay, so since AND is used, if all of them are true, then what we do? We add the corresponding coefficients. I am adding the coefficient of P1 with the coefficients of P2, and that is what is sum. Okay, and then this sum is attached to the resultant node. Which node? P3. I cannot use P1 or P2. I have to use what? P3 itself. P3, and attach sum and exponent of x, exponent of y and exponent of z. Okay, and I am additionally passing P3 again. Hope you understood. So this is the same thing what we did. If the exponents are same, because here we add only one exponent to compare, but in our example we have three exponents to compare. If all of them are same, then I add the corresponding coefficients and then do what? Increment P and increment P1 and increment P2. Same thing as we did here. See, So both the exponents are same. We add the corresponding coefficients, and what we are doing in the next slide. See here. So A is incremented and B is also incremented. Is that clear? Hello?
Yes, sir.
Okay. Now, yes. So if all are true, this is what we do. If any one is false here, we come here to the else if. Okay. And what I'm checking here is exponent P1's exponent, x exponent is lesser than P2's. Okay. Then what is that I do? I attach. Okay. P2's coefficient and see all these things. Okay. So you just compare the exponent of first term, that's all. X exponent and from the first term and of the first polynomial, and x exponent of the second polynomial. If the exponent of the first polynomial, x exponent of the first polynomial is lesser than the exponent of the x polynomial of x term of the second polynomial, then what you do? You attach the coefficient of the second polynomial and attach all the exponents from the second polynomial. Okay, and increase only P2. So you should not change the pointer P1. Pointer P1 should be pointing still to the same node, but only P2 can be advanced. Else if opposite, if this is not true, if the coefficient of x in exponent of x in P1 is greater than the exponent of x in P2, then attach what? Attach P1's coefficient and all the exponents of the P1. All the exponents of the P1. Is that clear?
Yes, sir.
Okay. Now similarly, so we are done with x. Okay. So set something like this. Let me write here. I'll write here. Say coefficient is 3, x to the power. Okay. Yeah, I can write it. X to the power 3, and then y to the power. I'll take it as 3, y to the power 3, and then z to the power 3. Okay. So this is one term of the polynomial 1. So similarly, I have to take another term from the polynomial 3. So what I did here, I compared all the exponents. So exponent of x, exponent of y, and exponent of z with the exponent of x, y, and z of the other polynomial. If they are same, then I do this. If this is not true, then I go for comparing the exponent of x with the exponent of x in the other polynomial. If this is true, then I attach P2's coefficient with all their exponents. Okay. Able to relate?
Yes, sir.
Okay. So now what I'll do. So similarly, this one here I'm checking if x is greater than, so the x coefficient in polynomial 1 is greater than the x coefficient of polynomial 2, then we do this. Okay, and increment only P1. So and similarly here I'm checking y coefficient of polynomial 1. If it is lesser than the y coefficient of polynomial 2, then we attach the term which has highest. Okay, so always, so go for attaching the term which has the highest exponent. Okay, so since y polynomial of P1 is lesser here, so you got to attach the term from the polynomial 2. See, the coefficient is from the polynomial 2 and exponent is also from the polynomial 2 for x, y and z, all the 3. Okay, and the same thing has to be repeated for all the combinations. Okay, so we have done it till here for the second case. Okay, P add we have finished. Okay, and then resultant polynomial and how to print that polynomial, that is what we need to discuss. So tomorrow we'll discuss it. Okay, and we'll go for executing this program also. Okay, so just I think I'll try to upload this program today to the Google site. So try to download it and just try to go through this program. In case if you get any doubts, so tomorrow when I come, you can ask me. Okay, so now I think it's already 4. We'll stop here.